What is reality? Another explanation of the quantum world. When we look around in our everyday world, everything seems clear and straightforward. There are solid objects, a table, a chair, the ground beneath our feet. These things have positions, they take up space, and they exist whether we look at them or not. This matches our common sense. But as soon as we begin to examine the world on smaller and smaller scales, first atoms, then electrons, this familiar picture starts to dissolve. Reality suddenly behaves in a completely different way. Let us first imagine a classical experiment. We throw tennis balls at a wall with two openings. Behind the wall, there is a surface that records where each ball lands. Each ball passes either through the left opening or through the right one. After many throws, we see two clusters of impacts. Everything is logical and exactly as expected. Now we replace the tennis balls with electrons. We fire them one by one at a wall with two very narrow slits. Behind the wall, a detector registers every arriving electron, always as a whole particle, never as a fragment. Electrons arrive as particles, but when we collect many of these impacts, we do not see two clusters. Instead, we see a striped pattern. Regions with many impacts alternate with regions that have almost none. This is exactly how waves behave. The pattern arises through interference, the reinforcement and cancellation of waves. What is astonishing is this. Even when we send the electrons one at a time, one after the other, the same interference pattern appears. The electrons cannot influence one another. Each individual electron seems to interfere with itself. To test this, we place measuring devices at the slits to determine which path the electron takes. Each electron clearly passes through one slit, never through both. But the moment we perform this measurement, the interference pattern disappears. What remains are two simple clusters, just like with the tennis balls. This means, when we observe the path, the electron behaves like a particle. When we do not observe it, it behaves like a wave. The act of measurement itself changes the outcome. One might suspect that our measuring devices disturb the electron, but quantum mechanics shows that there is no measurement gentle enough. Any measurement that determines the path unambiguously necessarily destroys the interference, and any measurement that preserves the interference provides no information about the path. This is not a technical limitation, but a fundamental law of nature. The question, which path did the electron really take, has no answer without measurement, not because we do not know the answer, but because the question itself is meaningless at this level. In quantum mechanics, we therefore give up trying to make exact predictions. Instead, we calculate probabilities. To do this, we use so-called probability amplitudes, which can be imagined as small arrows. These arrows have both a direction and a length. When an event can occur in several indistinguishable ways, we first add the arrows and then square the length of the resulting arrow. If the arrows point in the same direction, they reinforce one another. If they point in opposite directions, they can cancel out. This is precisely how interference arises. If, on the other hand, the possibilities are distinguishable, even in principle, we do not add the arrows but directly add the probabilities. In that case, no interference appears. This rule applies everywhere in the quantum world. It explains why crystals produce certain scattering patterns and why interference disappears in some processes as soon as information about the process could, in principle, be obtained. Another fundamental principle is the uncertainty principle. It states that the position and momentum of a particle cannot be determined simultaneously with arbitrary precision. This is not due to imperfect measuring instruments, but because particles do not possess both properties with exact values at the same time. This uncertainty is the reason atoms are stable. If an electron were located precisely in the atomic nucleus, its momentum would be extremely uncertain, and its energy enormous. This prevents atoms from collapsing. The existence of matter, chemistry, and ultimately life depends on this principle. The solidity of matter is also a consequence of quantum mechanics. When atoms are pushed too close together, uncertainty forces their electrons into rapid motion, creating resistance. That is why we do not fall through the floor. In the quantum world, energy is not continuous, but quantized. Electrons can occupy only certain energy values. When they transition between these states, light with a precisely defined energy is emitted or absorbed. This produces the characteristic spectral lines of elements, which allow us to determine the composition of even distant stars.